the equation over temperature, right? Later we will solving the Laplace equation or even the total heat transfer equation. We are actually solving the temperature. The final solution will be temperature a function of time and function of location, right? So that's the thing. Of course, they are actually similar. They both obey the first law of thermodynamics and the second law of thermodynamics. And the first law is actually comes of just the telling us the conservation of energy, right? And you cannot create it, cannot be eliminated, right? They only can convert from one form to another form, only transfer to one place to another place, right? The second law actually show the direction of the transfer, right? The different thermodynamics also, there's also some parameters we have to deal. The first one is actually, the first two actually most important, it's almost the same thing. Heat flux and the heat transfer rate. Smaller Q here, Q dot, and the capital Q dot. The reason why we have dots here because we are dealing with how fast the energy transfer. So actually, it's the amount of energy transferred per unit time, right? That's why we have dots there for the heat flux and for the heat transfer rate, right? Of course, we have three modes of heat transfer, right? We're dealing with the heat reduction, we're dealing with one parameter, we're using later will be the thermal conductivity, right? K and H will later studying the convection, so that is the heat transfer coefficient, right? Of course, also for the radiation, later we have the lemma for that. Next question. There are three modes of heat transfer, right? Most likely we determine which type of heat transfer occurs depending on the medium, right? The medium is solid. Most likely solid that we deal with here is the opaque solid. There was no transmission of light through the materials, right? So in solid we only have conduction. The heat transfer is observed by the just Fourier French scientist in 18th century. Yes. You can interested, you can Google his biography or just refer to the textbook, right? And just show that heat transfer rate, capital Q dot, actually the function is a linear function of temperature gradient, right? For the case, the temperature gradient dT over dx can be changed to delta T over delta x only when the temperature changes in linear, right? For example, you have the steady state without generation for the heat reduction to wall, right? In that case, if the temperature changes in linear, right? In that case, you have delta T over delta x equal to dT dx, right? Otherwise, cannot apply, right? Another form is actually the convection. It's named after the Isaac Newton, which is actually like a god in physics, right? After him, actually not because he is the observer of this law, most likely because other historical reason. The word convection just realized that it's not parallel to conduction. Convection, if you refer to the definition from the textbook, it's actually including two mechanisms, right? One is convection in liquid domain equal to conduction plus advection. Actually, the word convection, like the first three letters convection, the con it comes from conduction, right? The vection comes from advection. So with the liquid media, it's still there's no motion. So convection equals conduction, right? But if there is a motion, doesn't mean there is advection. In that case, convection including two terms, one conduction, the other convection. Later we will solving the equation. Later I'm not really solving the problem. You come to the such case, such second case. Like if the media is the water, right? If the water there is flow inside the water, then there will be convection, right? How about if the water is still, not moving? In that case, we are using conduction equation instead of convection equation. Remember the difference? But the other case, for the if the case is the medium is air, we never have pure conduction for air. You know why? Your air is gas. Gas that have thermal convection, right? As long as you have temperature difference, they will induce the flow. But the water, you change temperature, there are no thermal convection, so most likely there are no flow there. So no difference. Slight difference in depression in the Newton's law for we're describing the convection is not proportional to the term gradient. It's proportional to temperature difference between the surface and to the surrounding. And last law, another animation. Convection actually is almost the most important term in this class. Later you will find it's actually occupying about 5 to 4 chapters with dealing with purely convection. So if you can master the convection, then you can master the course. Otherwise you get trouble, right? Most important about convection. Because convection too simple. Radiation, in practice you won't encounter a lot of radiation. Radiation most likely is significant when temperature is very high, right? So in normal engineering we are most likely dealing with convection, so you should pay more attention about convection. Last about radiation. So it's actually you need the energy transferred by the electromagnetic wave, right? So described as Stephen Boltzmann law, right? Stephen, I think they both are Austria in 17th century, 18th century. So the name of Joseph Stephen and Ludwig Boltzmann. They both are big names in physics. Actually, most of them actually not physics. They are both simultaneously physicists and mechanists. So that's the difference. Another thing I can mention later, because we're talking about the conservation of energy, right? Then you have diffusive energy. So later we will deal with the Canals equation. We have a new parameter defined. This is alpha equal to k divided by rho Cp. Why we introduce this one? Because they are very similar to the units are same with the later we have mass diffusivity, right? Also have diffusivity of chemical species, right? Momentum diffusivity. So that's our actual equivalent. That's to describe how fast the energy can be transferred. Here, because we introduced 3 important parameters, right? The canality, the convection sometimes called the heat transfer coefficient, H, right? Of the diffusivity. You roughly know the magnitude for each certain materials to help you have an overall concept of what's the range of certain materials, right? Just for a simple, very simple example, let's say solving equation. The equation wants you to calculate about the heat transfer coefficient, the H value for the air. If you solve the air, you get the air, the H of air is over 100. That doesn't get wrong answer, right? You know for the free convection is from 2. Normally it's from 225. You get 100 for heat transfer coefficient in air. Doesn't get wrong answer, right? To know the concept and magnitude of this parameter for certain case help you to later when you solving equation of solving solution to verify your answer. Otherwise you get if you found the result is unreasonable, then you should check again, right? That's the thing. Sorry.
Yeah, can you slow down now? Because I think you're going too fast really. You're flying.
Oh.
We are all here in the earth. You are flying away.
Okay.
Yeah, can you slow down?
Okay. Another 2 very important concepts is actually, besides the 3 mode heat transfer, so another 2 is actually the energy distribution itself. There are 2 expressions. The first one is called the energy equation for the box. The other is the energy distribution. Actually, they both are same. Here just schematics show the concept, right? You have a closed system. Whenever we make closed system, actually, we just control volume, right? Anything can go in, anything can go out, anything can be generated, and anything can be eliminated, right? So that's the thing. Actually, this conservation of schematic of conservation can be applied for anything. If you input energy, then you have energy conservation. Inputting mass, you have mass conservation. The input is momentum, you have momentum conservation. Imagine that your bank account, you also have same thing, right? So the energy in can refer to as the month salary, right? Energy out is the monthly expense. The energy generation actually equal to the interest of the bank, right? The total change rate actually the number change your bank account. Very similar. That's the conservation law. In terms of energy conservation, so energy in is the heat transfer rate. Energy out also is the heat transfer rate out of the base. Q in and Q out can be represented by the three laws of the heat transfer mode, depending on the phase, right, of how energy transfers, right? By conduction using Fourier law, by convection using Newton law, by radiation using Stephan-Boltzmann law, right? All these things. And remember, the heat transfer rate is actually come in or come out from the surface. And the E generation, energy generation term, it actually refers to the energy generation per unit volume, right? It refers to the volume. Also, this storage changing rate of energy also refers to per unit volume. Another question I want to ask here. We're talking about what's the law of thermodynamics, right? Energy cannot be generated. And we have actually one term here, the third term, E generation. So, is that complete? Anyone? That can be taken count as one part of the participation for the course. If you answer the question during the briefing, it's fine. If you later answer the question, solving the question, it's fine, it's the same thing.
Could you repeat the question?
Yeah.
Yeah, that's the thing. We're talking about the first law of thermodynamics, right? It's mentioned energy cannot be created, right? But why in any advanced equation here, we have EJ here?
Change the internal state.
Sorry?
There's a change in internal state. Like, there's change in internal energy.
Yes, that's right, actually. Because here, we talk about the thermodynamics, we're talking about the different form of energy. But we're talking about the heat transfer here, we're only talking about the heat, internal energy, right? E generation here, actually, is the other form energy converts to internal energy or internal energy converts back. So it can be positive value, can be negative value, right? You know that there are no conflicts here.
Then you already start with the change of state. So like this.
That's from the name side. Okay.
I don't know. So I do.
A very specific form.
Oh,
We are choosing the control the volume in different way. I mean, along the surface, very narrow surface, you have to define the area A, is the final value, but the depth going to approaching zero. In that case, we will also get the volume, the dirt volume approaching zero. In that, as just mentioned, E generation refers to E generation per unit volume. If I don't have volume, you don't have E generation, right? Another thing, this delta E also refers to the energy storage changing rate per unit volume. So you don't have volume, the last term also changes to zero, right? In that, you have a different equation. So E generation equal to zero, delta E equal to zero, then you only have energy in equal to energy out. Why? Because when you truly control the surface, there are no energy can be stored or no energy can be get out, right? So no energy can be stored and no energy can be generated in such a small volume, right? Approaching zero. That's another. Actually, they are considered they are the same. Actually, any equation for the bulk and any equation for the surface, they both are same. For the surface, only one specific case, only when the volume approaching zero. In that case, you have energy in equal to energy out. Here just schematic to show a very simple case, right? When choosing the control volume, along the surface, you have control the surface. So in that case, energy in equal to energy out. So energy in, as I mentioned, Q1 equal to conduction can be expressed by the Fourier law, right? Then Q out, the actual combination of two terms, radiation and convection, right? Equal to Q2 plus Q3, the Q2 represented by convection, represented by Newton law, Q3 represented by Stephan-Boltzmann law, right? The substitute equation we just learned here, right? So that's the thing. Remember, here is no difference. Convection, actually not parallel with conduction. Particularly with the medium is liquid, or just liquid. It's the gas, right? Convection can including both conduction and advection. But radiation and the convection are parallel, right? So that's the concept. Later when you analyze the question, you know the thing when the medium is solid, we only have conduction, right? But when the medium is liquid, it's our gas. We have convection. On top of conduction, we may also have the radiation. So that's the thing. Because this is a tutorial class, most likely my responsibility to help you pass all the quiz exams, right? So there are some solving techniques for solving the problem, right? There are a few very general steps. Actually, I summarized the steps based on our marking regime, right? The first step, you get the first score for each problem, otherwise the trouble, right? First thing, of course, you should withdraw all the information, the useful information. Particularly, it's the we call it the useful mathematical or physics information, right? Other thing in description in text, actually not important, right? Most likely from the number, right? Then draw schematic, right? Then also just list all the information in the schematic. Then you should summarize all the assumptions here, right? Apply the physical law. Then substitute all the number, get calculation. Then once you get calculation done, get the number, right? The last step, you should reading the number, verification number. That's why we call why I introduced it here. If you know roughly the magnitude for each case, then you know how to verify your answer, right? For each case, if you get the wrong, you do the calculation, but the number is unreasonable, you go back to check, right? That's the reason why we should give you the concept of magnitude, right? Okay, another thing, the last thing, the important note. First thing, you should attend all the lectures of the class, then solving all the questions before you come here. And if you are willing to come here and present the results to the fellows, then get credit for that, okay? Roughly, that's my summary of content for the lecture last week. And remember, the tutorial class is always one week late compared to the corresponding the lecture, right? So today's content actually corresponding to the lecture last week, right?
Oh, so it's conduct and combat. A bit of combat.
What? The first chapter is all three. This is the intro. After that he goes to start, then go
Oh,
combat. Yeah, but you do know our prof now keep up with pace.
Yeah, I know.
So it's,
Okay.
it's going to be like behind quite a lot.
Then we're going to our core part. Actually, it's the solving unit 5 or 6 questions for each studio class. During the session, I ask students to come here voluntarily to personally read out to others. Okay, let's go one by one. Actually, they update this question every semester, so I realize there's a lot of difference comparing with the last one. Okay, as I mentioned just now, I showed you one slide that showed how a standard technique to solving this question. The first step we call the problem statement, right? Try to withdraw all the useful information in the text part, right? All those things are non-useful, right? All the useful things here, there are 2 feet, right? They give you the dimension of the feet, right? The width and length, right? This is actually the 8.
Number one.
We give you the thickness, right? Useful information, this one. And the temperature, one side giving you, temperature on the other side also giving you. Because this is actually from a problem of pure conduction, right? Very simple. The question asks you, estimates the rate of petrol loss. Actually asking you to calculate the capital Q, right? Or Q dot. Actually, because we're all using Q dot in this course, sometimes you can directly using Q instead of Q dot. Because they are all Q dots, right? Very simple, pure conduction. So any volunteers?
Do you have a marker?
No, the marker. I have the camera here. You can directly show you the answer. You also have the. If you prefer the marker side.
Question 1 is the easiest already. Question 1 is the easiest already.
Okay, so it's conduction.
Actually, it's more fun now.
It's not from.
It's going to be very small.
of this
so high.
and one of this is 30. So because they are vastly bigger than 0.5, so we can use it as a one-dimensional kind of heat transfer. So we have two temperature. One is lower temperature, which is 0 degree Celsius, and this part is 37 degrees Celsius. So it's a simple Fourier's theorem in a way. E areas, delta T over L, something like this. And area, we just take notice 2 of the 10 times 30 times 2 because it's both feet. And we have K is given here, the thermal conductivity of leather. We have A, we have area because from 10 times 30. We have delta T, we have L. So if you plug in, you should get 6 watt because I didn't calculate that, but yes, we should get that. And the total rate of heat loss from the human body, I guess I'll just Google, but I didn't. Discuss all possible modes of heat transfer from the human body. Very lousy drama, so bear with me. Definitely convection. Convection and radiation. I think these two.
Yeah.
Well, possibly conduction if you have to touch something, I guess. So I think that's probably it.
Then another one, if you are, the weather is hot, you are sweating, then you have the condensation heat transfer. Right? Then
Yeah.
you are studying that. This is not a different form, but sometimes
It's still
yeah,
convection, right?
yeah.
It's still kind of included in convection.
It's a convection with H equal to floating to infinity. So that's the specific, right? But still right. Another thing, usually when we draw the schematic, we have the, like I said, in this case, you have the feet stand on the ground, right?
Yes.
Most likely we draw schematic horizontally, right?
Sure.
Otherwise it's just fine. That's actually fine. Just can further improve that.
Yeah,
Yep.
the guy.
It's not a common way of those things.
Yep.
Another thing, when you calculate the result, we need to convert all the units to SI unit.
Yep.
Like we have dimension 10 cm, 30 cm, we convert to meter, right? Otherwise the unit might trouble, right?
Yep.
Very
But,
good, thank you.
yeah, but LT is fine because
Yeah, I
it's
understand.
delta. So,
限制。
So any different opinions? Right? It's a very simple question, this one. Remember, when you're writing the Fulling law, there are always a negative sign there, because that indicates the direction of the transfer, always from high temperature to low temperature. That's why we have negative sign there.
So what are the assumptions that are made in this question?
Yeah.
There's only one assumption.
Yeah, that's quite later I'll show the standard answer, not actually my standard answer.
So that so the assumptions.
maybe also like constant properties, and the one-dimensional like heat transfer. That's the two.
Yeah.
Yeah. And then
The steady state, no dimension, no conductor resistance, right? There are quite a very common 3 or 4.
yeah.
Yeah, that's our pattern.
哎呀，你还不稳定。
That's a very good answer, but that answer cannot get 100% for the credit. The reason why, because we have the standard regime for the answer, right? So first we call the formula statement, right? This is the given, right? And the question asks you found something, and here easily, right? Just calculate the section rate, right? As I mentioned, because through the course we all calculate by the head flux or total rate per unit time, right? So instead of using Q dot or capital Q dot, we just directly using Q or capital Q done method. Assumption, here just I think 5 very common assumptions during the course. Just remember, when you write assumption, we try to using as simple as possible. Just a few keywords. Where the marking can give you the point. Write a long sentence doesn't make sense, right? The steady state, one deconduction action comes the material, most likely comes the material property, but here we only deal with the conduction. So the only material property we deal with is conductivity, right? No condition and constant resistance. There's another one also, later you will find that it's the ignitable radiation, right? No radiation, so Let's see another one. One thing I want to highlight, whenever we're talking about the one-dimensional assumption, we're talking about one-dimensional heat conduction. Because the convection radiation actually pointing to the other direction, cannot be one-dimensional. So that's the only thing. The solution is quite simple. Just now students show the right answer. Just remember to convert the unit to our SI unit, right? Apply Fourier law, directly answer. Simple. As I mentioned, that's the special case when we have the dt over dx actually equal to the delta x divided by delta x, right? Delta t divided by delta x. Same thing, because the temperature change is linear, right? Otherwise, if the temperature change is not linear, you cannot apply. Original Fourier law can apply, but cannot equal to the delta x divided by L. That's the difference. Because last few semesters we are marking the particular first quiz 1. We have temperature difference given the temperature distribution and function of temperature distribution at the location as a function of x, Tx. The question asks you to calculate about the transfer rate. You cannot using the delta x divided by L, you must use the dt divided by dx. Because when the temperature is not linear, you cannot using that one, right? Just a very special case. Later they ask you compare with the ratio of heat loss for the whole human body, right? Just this value I think I found this value by Google or in the textbook, I don't know. They compare, they get the ratio, that's the thing, right? Okay, let's go to question 2. Actually, it's given you already, right? There are two different materials aligned, right? Constantly, not constantly, aligned. I'm not sure the double row device. Okay, the conductivity given here, we are dealing with the formula part for the heat conduction, right? Simple. There are two of them couple. Giving you two temperature difference, right? The question asks you to derive the formula to computing the Kb, the conductivity of another material based on the conductivity of given material, Ka, right? That's the thing. Again, it's a purely conduction problem. Schematic given you, right? Just this assumption apply the physical law here. Given defining the physical law here, there should be the Fourier law, right? Very simple. Only case you should apply the Fourier law twice. For section A, for section B, then they have continuity of the flux. That's the same question. Another thing, before we ask students to help here to present the result, how many of you know, as a new students, what's the mechanism of the couple? How it works? It's a very, what's the mechanism? How mechanism of the couple? And how the couple works?
The whole resistivity.
You are from a new background, right? The couple.
Change of current change of current from one point of neutral to one point of contact.
Right.
Your thermocouple is one point of neutral and one point is contact of the heat. Then the change of current will be a difference of temperature.
No, that's the most deeper in the physics. The couple, the effect they call the feedback effect. The thing that when you apply the electric potential, they are giving a temperature difference. Or going back, when you have a temperature difference, they are giving the electric potential. You can measure the electric potential. They can calculate the values. Given what temperature, they give me what potential. They get a plot. Then when you measure the electric potential, you go back to plot one temperature. That's how the couple works. The origin they call the feedback effect. If you're interested, go back to Google roughly. Because any student you know, they have different type of sensor to measure the potential pressure, measure potential, to measure the density, measure them conducting something. You should roughly know how to work, right? Okay, that's the thing. As I mentioned, the pure conduction problem. So any volunteers? Okay, no, just one for everyone. Okay. And again, it's a very simple question. The schematic already given you, so you don't need to draw it yourself, right?
Nobody volunteers.
We do every tutor are given the standard answer, but we actually formulate our own version of the result. For me, because I prefer this simple style, I just using as the simplest word to get the answer, right? Again, proper statement, right? They give you all the distance and temperature, right? Give me one penalty for section A. They ask you from the KD as a function of KA and the dot A, dot AB, dot T, dot TB, right? Again, because quick junction, as I mentioned, those assumptions are quite universal. Of course, some cases doesn't apply, but then just remove, right? Again, because the boundary are perfectly isolated, right? There are no flux. But also, you have continuity of flux, right? QA equals QB, then apply the Fullian law for both QA, section A and section B, right? Remember here, for this equation, the second one, only KB you don't know, right? So for them to derive, get KB as a function of KA and another thing, right? Very simple first impression. That's actually the standard approach for way to measure the local conductivity for unknown materials, right? Given the materials for, we know local conductivity for one material, based on this equation, we can obtain the local conductivity for unknown materials. That's the common approach for way to measure the local conductivity, right?
Sir,
So, how come what come you took away the A?
Sorry?
Why's the A disappeared?
Assume same.
What's the A?
Yeah, it's because
My answer.
there's an A missing, right? So how come you took away the A?
Where is the A sign?
Yeah, you see the the area.
Oh,
Yeah,
the same area is gone, right?
but you didn't say it's two identical.
Oh, yeah.
How do you know?
Because you see the schematic, they show exactly there are two same cylinder aligned together. Right?
Just assume. Okay, can.
That's the same because of.
I mean, because you didn't say it's identical, so you can assume it's two
Yeah.
different area. Then you also don't.
I understand the question. If you the actual two section area A are different, can still solve that, right? It's simple. Then you get one A here, A1 here, right? Sorry. A here, AB here, right?
Okay.
But still can solve, right?
Okay, can.
But the final solution may be different. They have I think B over A, right? The same thing. Sometimes they give you the schematic already show very clearly some information are given, right? This is because this is a new question, given just this new stuff. So might be some problem, not very consistent, but yeah.